All right, so last time we met, we introduced ourselves to power series. These are essentially functions that are polynomials of infinite degree. And, well, you could express these in sigma notation. And if you, would take them out of sigma notation, you can see how they look like polynomials of infinite degree. Because you've got this constant term, this coefficient in front of the degree 1 term, this coefficient in front of the degree 2 term, and so on and so forth. Now, for a power series of this form, what we learned last time was how to identify the center of the polynomial. Here, the center would be x equals a, because if you plug in x equals a, that would wipe out all of the terms degree 1 and higher. And the general coefficient is just the phrasing of the coefficient that lies in front of the x to the a. So in this case, the general coefficient would just be Cn, whatever that happens to be. Okay, sweet. I would like to talk now about a notion relating to power series, which is called radius of convergence. And radius of convergence is essentially the distance from the center that a power series will converge within an open interval. Now, hold on a second, because there's a couple things to think about here. Here we're talking about the convergence of a power series. Well, if you look at this expression, and you imagine different values plugged in for x, it's conceivable that at the center, the power series would definitely converge. Because if you plug in x equals a, you get a bunch of zeros for these terms of degree 1 and higher. And the only thing that's left is the constant term. And certainly a constant term is a number off the number line. So yes, if you plug in x equals a, this is a function, right? You could plug in anything for x. If you plug in x equal a, you will get a series that is definitely convergent because in fact it only has one non-zero value in it. Now it is also conceivable that depending on the values of x you plug in, this series might have a hard time converging. This series might have a hard time for its sum to remain finite. Because if you plugged in conceivably, if you plugged in a value of x here that was very different from a, then what's in this parenthesis would be very large. And if what's in this parenthesis is very large, then that might be causing our sum to turn to be an infinite in value whenever we add it up. And, well, it's conceivable then that a value of x that differs from a by a lot could be a value from x that differs by a from too much for our power series to evaluate to be a number on the number line. And well, that would mean that our power series would diverge. So when we talk about a power series converging, we want to know the values for x where the power series would converge. And well, one notion related to this is what's called the radius of convergence. So as we've discussed, the center of the power series we know will be a point where the power series will converge. You plug in a, there's no doubt the power series will converge there. However, as we mentioned, it's conceivable that the farther you move away from a, the harder the series is going to have to converge. And in fact, as it turns out, and we will see why this is the case, that the radius of convergence will always be the distance from the center to the outside of an open interval where the power series will converge. So in fact, the power series will always converge around on an interval that will be symmetric to the center of the power series A. So it'll go some number of units to the right and some number of units to the left, this open interval of convergence. And this open interval convergence we could write out as a minus r, a plus r. So a minus r, the center, take away the radius of convergence, and a plus r, the center, plus the radius of convergence. Right, so the question becomes, how do we determine the radius of convergence of a power series? Because if I'm looking at a power series, and say I even know what its constants are, well then how can I determine precisely the values for which the power series must converge? How can I determine the sort of width of this open interval that would on which the power series would converge? Well, in fact, we're going to use the ratio test to show how. So let's consider this. Let's consider a power series that's of the classic form of our power series. We're going to apply the ratio test to it. So when we apply the ratio test to a power series, Well, just like when you apply the ratio test to any series, you just take the limit as n goes to infinity of the n plus 1th term over the nth term. Well, in this case, what is the n plus 1th term? The n plus 1th term is just going to be c to the n plus, or c sub n plus 1, and then x minus a raised to the n plus 1th power. And down below, the nth term will be just c sub n times x minus a to the n. Now, noticing that there's a bunch of factors of x minus a upstairs and downstairs. In fact, all of the factors of x minus a downstairs will cancel, leaving just a single factor of x minus a upstairs. If we look at it like so, we could actually sort of separate out our statement here and bring our x minus a term separate from the cn plus 1 and the cn, the constants that are in front of our powers of x in our power series, and we'd essentially have the exact same statement. Now, this is what comes out of the ratio test. Now, what do we want to have happen? We want to assess convergence of our series. Well, to assess convergence of our series, we're going to have to set what pops out of the ratio test to be less than 1. Because remember, back to the ratio test, the limit associated with the ratio test yields a convergent result precisely when you have less than 1 for the value of that limit. So we want to find out when this limit is less than 1. Now, because we've separated things out with this x minus a by itself, we could actually solve for x minus a. And if we did solve for x minus a, we could just multiply, or rather divide both sides by this limit. Note, by the way, this is an absolute value here. So if we're dividing by this limit, that's perfectly acceptable because we're dividing by a positive thing. We don't have to flip this inequality sign at all. And so we'll get x minus a is less than, the limit as n goes to infinity of cn over cn plus 1. Now note, when we divide by this fraction, you know what? Dividing by a fraction is like multiplying by its reciprocal. So whenever we divide by this limit and bring it to the other side, the reciprocal of that limit would be, well, the cn in the numerator and the cn plus 1 in the denominator. Why don't we have to have our limit still over here on the left? Well, because this expression x minus a doesn't even depend on n. So ultimately, this has nothing to do with n, so this will just be x minus a. And what's on the right will be, well, what we'll have on the right as the value for which the power series would converge using the ratio test. Well, I want to take this inequality and view this inequality visually because looking at this inequality, like if x was equal to a, the left-hand side would be 0, and clearly 0 is less than what we've got on the right-hand side. But now, if what's on the left-hand side would not involve x equals a, it's possible that depending on what this value of this limit is of this cn over cn plus 1, that the larger the value of x, the harder this absolute value on the left-hand side is going to have being less than whatever that limit is. So presumably, there's going to be some value for x that we plug in to where the value of this absolute value on the left-hand side gets too big. And whenever you look at these absolute value inequalities visually, it eventually ends up taking this form always. So we've got this center at x equals a, and then some distance away to the right and to the left. In fact, the distance is going to be precisely dictated by what the limit is on the right-hand side of that inequality, what the value of that limit is. Well, then here is the solution to this inequality. But wait a second. What we have produced is something that looks extremely similar to something that we looked at previously. Because we were previously looking at the interval of convergence of a power series. And we were showing that the interval of convergence should be an interval that goes r units to the right of the center and r units to the left of the center. Well, as we were solving this inequality down below, what we noticed is the distance that you go to the right of the center and the distance that you go to the left of the center is precisely the limit as n goes to infinity of the general coefficient over the general coefficient of the n plus 1th degree term. But wait a second, that means that the radius of convergence r is just precisely this limit. And in fact, that's exactly what we've got written down here. The radius of convergence of our power series is just the limit as n goes to infinity of the general constant over the general constant of the n plus 1th degree term. And this is going to coincide precisely to our notion of r, which we had written out previously. So the radius of convergence is simply this limit. And in fact, then, from this, we could produce the open interval of convergence, which is going to be all values between a minus r and a plus r. So if you let this limit here be equal to r, then you get all things between a minus r and a plus r. And those will be all values for x, where our series, f of x, will be guaranteed to be a number off the number line. If, on the other hand, we plug in a value that is outside of this open interval of convergence, to the left or to the right of its boundary, we would be plugging in a value where the ratio test would evaluate not to less than 1, but rather to greater than 1. So the values for x that are outside of this open interval of convergence, or outside of the boundary of its open interval of convergence, will correspond to where the ratio test yields a greater than 1 result, and the series must diverge. On the inside of the radius of convergence, we will have the less than 1 case, and that is what we refer to as the open interval of convergence. It's going to be all values between a minus r, a plus r. Now, I realize this has been a lot of technical language with a lot of symbolic usage throughout. What I'd like to do in the next video is hit an example just so that we can see this radius of convergence more concretely manifest.